So this will be the assignment. I believe it's 3. And we're doing question 1. And what question 1 is asking us to do is to essentially revisit in the notes. There was 10,000 particles. There was 5,000 units of energy available. So the 10,000 particles have to use up all units of energy at all times, and each of the particles only has 3 energy levels. So the first energy level, so if you're a particle who's in the first energy level, you have 0 energy. If you're a particle that's in the second energy state or level, you hold 1 unit of energy. And of course, there's the third that you hold 2 units of energy. So you can almost think of 2 extremes for the 5,000 units of energy and the 10,000 particles. So one way to look at it, one way would be to say, what if all of the energy was used up by particles in the third energy level? So each particle would use up 2 units of energy, which means you could say one extreme, if you had 2,500 particles in the third, right? ... Obviously, they would use 5,000 things of energy. And then, therefore, where do all the other particles have to go? If 2,500 particles were in the third energy level, they would use up all of the energy. So therefore, the number that were in the second energy state would have to be 0, because the second energy state uses 1 unit of energy. And if all of the energy goes to particles in the third, then that means the remaining particles would be in the first. So that would be 7,500. So you can almost see how, if you're starting to try and graph the distribution of the particles for all of the situations, one extreme on the graph is going to be if all of the energy was used up by particles in the third level, that means I'd have to have 2,500 of them to use up the 5,000. There'd be none in the second energy level, so that number would be 0, and N1 would be 7,500. So that's one extreme. Another extreme, to try and simplify this a bit as well, would be to say, what if there was none in the third energy level? So think about that. It's only the second level that has any energy value. The first has 0. So I have to use up 5,000 units of energy, and if hypothetically none were in the third energy state, then that means I'd have to have 5,000 particles out of the 10,000 total. That would be in the second energy level. Because if I'm a particle in the second energy level, we each hold 1 unit of energy, so therefore 5,000 of us would hold 5,000 units of energy for the system, so that's good. And therefore, because none were in the third, all of the remaining 5,000 particles must be in the first energy. So the remaining second. That is correct. I'm talking myself sideways. So if we said 5,000 were in the second energy level, using up the 5,000 units of energy, the remaining 5,000 particles would have to be in the first, which holds 0. So that makes sense. So you'd have 5,000 in the second, 5,000 here. So there's a couple of ways we could look at it. This extreme is going to be easy to fill in a little chart here to say, if we're claiming 5,000 were in the second energy level, so the numbers is that, and each of them uses up 1 unit of energy. So therefore, all 5,000 units of energy are used up by the 5,000 in the second. We know that there would be 0 in the third, so there's no energy used up by any of them because there isn't any. And the remaining 5,000, because there's 10,000 total, have to be here. So that'd be 5,000, 0. So let's track the total energy, which we know always has to be this. So technically, you can see in this chart what's going to happen. The number that are in the second contribute to energy and holding it. This first one has none, so that's why you can almost forget about it for summing up total energy. 0 in here, so I'm always going to be adding these two numbers to get this. So now watch what's going to happen. If we start trying to say, okay, let's start, so I think our graph is going to track on the x-axis. I do believe, let me double check real quick. Yeah. So our graph, and this is what we're kind of thinking ahead to. Our graph is looking at some concept of, there's a way to call it weighting or numbers of particles. But let's say that our x-axis is going to be the number that's in the third. So this is an important number that we're going to be migrating towards. So we want to work out a relationship here. So what if I said, let's take 1 away from this. So let's say you have 4999 numbers in the second. That means you have this many units of energy, right? Let's watch what happens. Well, I take 1 away from here, and it's given up 1 unit of energy. So here's the problem. If you give up 1 unit of energy, the third one requires 2 units of energy. This one requires 2 units of energy. This one is only 1, and this one uses up 0. You can't give 1 to this because it needs 2 units of energy to be a particle in the third energy state. And you can't give it here because we're told all the particles have to hold all the energy. So what we're realizing is this doesn't work. What if I take 2 away from this? So the system can't have 4999 particles in a second. Can't be. But what if we took 2 away? So 2 of these go away, which means the amount of energy tracks that, right? Now, think of it this way. Now 2 units of energy has been freed up. This takes 0, this takes 2, so technically we have to have the particles hold it, so we have to increase this by 1. And then you get 2 units of energy. So when we add these two, we're back to using up the 5,000 units of energy. But notice, 2 particles leave the category of being in the second energy state. Now you have 1 particle, but we need the total number of particles has to get back to 5,000 as well. So therefore, 1 of them has to also go here. But it holds no energy. So we see what's going to happen here. And this is the other thing. So this is an interesting way of looking at this extreme. So let's go back here for a second and think about it. One of the equations that holds true, and we could have put N1 here or N3, but the point is, the number that are in a second energy state, for instance, we have 10,000 particles. If I knew the number that were in number 1, and I knew the number in 3, you take away those 2 numbers from 10,000, you'll get this. So this is an easy equation to understand why it has to work. But down in this chart, we noticed there's a special relationship between N2 and N3 because of the relationship with the energy. This number in the second has to change by increments of 2 particles. And a change of 2 particles from n equals 2 automatically has to give 1 to n equals 3 and 1 to n equals 1. That's the number of particle number. But related to that is the energy. So a change in 2 particles of 2 frees up 2 units of energy and automatically has to increase this one by 1 because of the 2 units of energy. So when you're looking at this, you could say to yourself, If the number in the second one has to change by 2, one goes here, one goes here, but this has no energy. So therefore, what essentially happens because of this, any change in the number, and notice how we started at this magical point right here. We started with 5,000. So now we're going to build a completely separate relationship, a little bit separate from this, right? So that's one equation. Now we're going to this chart and we realized if there was none in n equals 3, there'd have to be 5,000 n equals 2. So that would be true. But neglecting n equals 1 for a moment, because we're starting with this 5,000, and that's where this comes from. 5,000 here means there's 0 n equal 3, third ones. If we drop this one by 2, this only increases by 1. So in other words, if I give 1 to n equals 3, what did you change your second energy number from 5,000 in this chart? Well, this has to change by 2. So therefore, if I was to increase, if n equals 3 equaled 1 particle, the change that had to take place in the number of them that were in the second state has to be by increments of 2. So this equation is very specific, being built from this fact of the system, where we started with 5,000, there was none here. So if I put 0 here, right, if I know n equals 3 is 0, then obviously 5,000 has to be n equals 2. So this becomes like a second equation, and this is how and why this has to be true. So you can see how this is a very simple example with just 3 energy levels, and they chose it purposely this way so that we could work out a couple of equations for the purpose of demonstrating the dominant configuration. Start with something simple like this, and that you can very clearly see what's going to happen when you have a mole of things and you have more energy states. So this is how we'll start. This is where we get these 2 equations from. Okay, so what we're going to do next is, and I'm going to take some of the pages from my notes, and this might change a little bit over time, but the content of what I'm showing you fits perfectly with this question. So remember how we started out, and we pointed out there's 2 extreme cases for the graph that we're trying to build. Now what's going to happen is we're going to be looking at the ln of what's called the weight. We'll come back to that. Weight is related to, essentially, there is a relationship between the weight of something with the number of ways you could arrange a particular configuration. So we're looking to make a graph that's kind of like this. So obviously if n equals 3 was 0, right, we did that here. And what that means is there's going to be a number of ways the system could be arranged. So let's think about that. If the number in the third is 0, all you have floating around in your gas sample, for instance, is 5,000 who are in their second, 5,000 who are in the first. But how many different ways could you make this? If you magically, like Maxwell's demon, so to speak, if you could magically keep track of all 10,000 particles and give them their own little serial number that only you could see, how many different ways from numbers 1 to 10,000 could be the ones holding the 1 unit of energy each? That is a very large number of different ways. We can't distinguish, like Maxwell's demon. We don't see all of the 10,000 particles and can clearly see who exactly is holding it, right? So it's almost like double counting in statistics. So if you had a dice and you were looking at, if you had 2 dice, for instance, 2 die, and somebody said you identical dice, you roll them up, how many ways can you have a 1 and a 3? Well, Maxwell's demon might put a little tiny mark on the die, A and B, right? But if you can't see that, and you can't distinguish between the 2, well, you can have one of the dice being the 1 and the other being the 3. But without me knowing it, the one die that one way of doing it was a 1. What if it was the 3 and the other one was the 1? So we would say there's 2 ways in a 2 dice system. If I show a 1 and a 3, there's 2 ways of doing it. I just don't know which dice is which. So this is the concept of how many ways to do that. So you can only imagine, right, 10,000 particles, 5,000 of them happen to each be holding one unit. But how do I know which is holding which? So the number of ways you can arrange a system when n equals 0 is going to be a very, very large number. The other extreme was if all of the energy was used up in the third energy level. So that means 2,500 particles would be in the third. So if N3 was equal to 2,500 would be the other max, right? And the number of ways of arranging the system for that would probably be smaller than that would be here. So what's going to happen with the graph is you're going to get some sort of, it's going to look like this. So the question is, what is that magical number in the third state that give rise to the largest number of ways to arrange the system, right? That's a special, and you can see in calculus, right? It would be where the slope of this graph is equal to 0, or the peak or the maxima. That's essentially what we're looking at. So we've got two extremes here. If n equals 3, if the n3 number was 0 or it was 2,500, somewhere in between will be a configuration, right? And you can see right here. So what we're going to end up doing is we're going to build onto the graph tracking the number of ways or the weight of the configuration, right? That's what the y-axis is going to be. So we could start with this one. So we're going to look at the one extreme where all of the energy was in particles in the third. So 2,500 was your n equals 3 number, okay? That means there was none in the second energy level, and all the rest were in the first, okay? So how do we calculate using statistics the number of ways to arrange the system if n equals 3, or n3 was equal to 2,500? So the formula comes to this. The weight of the configuration is the total number n of the particles, exclamation mark, and we all know what that means. So for example, if somebody was to write down the number 4 factorial, right? That means take 4, multiply by 3, multiply by 2, multiply by 1, right? Now imagine if this is 10,000. 10,000 times 9999 times 9998, blah, blah, blah. That's a big number. Divided by the number that were in the first energy level, factorial, times the number in the second, times factorial, times the number in the third. So it would look like this. Now, none of these can be done by calculator. And I think the calculator, I don't know if it caps out at 70 or is it 120 or something like that. So you can't calculate these in a calculator, which is a problem. So the Stirling approximation is a tool to calculate this number, sort of indirectly. So they take the ln of both sides. So you can clearly see that I'm looking for the total number of ways to arrange the system in this configuration that was specified here. Too big, can't do it by calculator. So I'm going to take the ln of both sides. So now I'm going to track the ln of the number of ways. And you can see how this breaks down. This would be subtract off these ones, right? And I'm just taking a quick look here. Yeah, the Stirling approximation is that when you have the ln of n factorial, you can replace this with n times the ln of n. So this is a way to approximate closely what this number would look like, because you still can't calculate this in your calculator. You would have to type in 10,000 factorial, which will go error. So this is algebraically approximated with that, this with this. So this is the trick of how to go about calculating it. So in the current case, we know that n was 10,000, so we get that number. We know that n1 was 7,500, so we get that number. This one was 0. This one was 2,500. So the ln of the number of ways a system, because we can't keep track of all those damn particles, the number of ways you can make it is 5,625. So what we're going to do here is, that's the ln. Take both sides to the e. So that gives us W, the weight free, E to the 5623. So this is the official number of ways you could arrange the system to achieve 2500 are in the third, 7500 in the first. Oh my God, that is a very large number of ways just for that one configuration where N3 is 2500. Okay, so you're seeing the gist of how this flows. The other extreme, we talked about it, was if N3 was 0. So that means N2 would be 5,000, N1 is 5,000. We use that formula in the Stirling approximation, we get the ln being that, so therefore, put both sides to the E. It's E to the 69331. Oh my God. So look at what we've compared here. This one, the ln of the weight is 6931. The other extreme was 5623. So you see what I did here in this little chart? I quickly approximated the two extremes so that when I make this graph of ln of W, right? So the one extreme was N3 equals 0 right here. So you see how that was 6931. The other extreme was when N3 was 2500. The ln of W was 5623. So do you see how I set it up this way? And all I did was I picked off, just for the heck of it, a few numbers in between. So you can see how high the ln of W is getting. And it turns out that there will end up being a max. I could do this by attrition in Excel. So I want to make this number right here as big as I can by arbitrarily choosing N3. And it turns out later, as you'll find using Excel, it's going to turn out at approximately, there's a number down here, but you'll get this y-axis being 9013. That's big. That's a big number. Right, so I wrote down here, it turns out when I used Excel through attrition, you can prove that when N3 is 1162, then the ln of W, that's your maximum number of ways of doing it, was 9013. Now a lot of people can get the same answer, or I'll take 9011 or 90111 or something like that, very close to this. As long as the graph ends up looking very much like that, you're proving it to yourself, we get to here. Okay, so now when you go to Excel, and you can see how what I've done here in Excel is you have N3, N2, N1. We've already showed you how you can calculate using the Stirling approximation the ln of the weight. So clearly what you're going to do is under n equals 3, and let's see if I can zoom in here a bit, make it a little. So I started off at, this is only, folks, a small portion. I started here for this is only a part of my Excel spreadsheet. And I purposely was through attrition typing in more and more numbers so I could prove to myself that the ln number would max out just by looking down the chart. So you see here at N3 was 1000. Ln W was 8979. So I'm going along and I'm tracking this and I'm looking here so you can see, look at this, this is 9011.69. That was 1148 was N3. Then I go to 1150, 9011.76. So I'm tracking, when does this number get the biggest? So according to mine, right here, 9011.943, and that was when it was 1162. But see how I populated the next one was 1163, going up 1160. So technically, I guess I could arguably say, what if it was 1161? We don't have to get quite that good, but I narrowed it down plus or minus 1 or 2. So the maximum ln W value is 9011.943. You could call it almost 9012 or something very close to that. And the number for N3 was 1162. So you can see here, back here, I went back to this graph and I said I found out using attrition in Excel, N3 at 1162 gave me and I put 9013. Technically here, it's actually 9012, right? So, but it's close enough. So that's how I knew I could label that point. This is the attrition part. But now what we're going to do is add a column. We're going to look at the actual W divided by W max. So how did I do that? Well, I want to make a second graph, right? The second graph is going to be the W value divided by W max. And because I can't calculate either of these two numbers with my calculator, is there another way of doing it? And here's the trick to get this graph. So you're going to have on your y-axis W divided by W max. You're not going to have these two values separately, but you'll have this quantity, right? So let's do an example. If I had N3 equal to 1,000, I already knew that the ln of W for the 1,000 was 8979, okay? So I'll put I didn't show the step here, but do you notice the ln of W would equal 8979? But if I put both sides to the E, so if I went E to the ln W equals E to the 8979, we know that this one would be W equals E to the 8979. So E to this exponent becomes W. So I put that in the numerator. In the denominator, I know that the W max, we already knew, would be E to the 9011 or 12. So now you can use this, the same base, you subtract. So what you're going to end up with is 1 over E to the 33. This becomes the quantity W divided by W max. This would be a number I put on the y-axis. So basically what you're doing is you're going to graph x-axis N3, and over here the quantity E W over W max, which will come from the form of this kind of subtraction. This you can calculate. And see, 10 to the minus 15, it's almost 0. So what you're really going to do is you're going to end up with something. All you're looking to do is graph the pattern that Boltzmann was trying to. Let's see if I can bring this back. Ding, ding, ding. Boy, I'm having trouble with the getting at this button. Okay. So this is a graph of W divided by W max. We just showed you how to do that. The x-axis is N3 numbers. So you're going to focus right in here. Ding, 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 right? You know, between N3 is 1,000 and 1,300, because that is where you get this sharp peak. And any other value of N3 from the smallest number, which would be at 0 up to 2,500, you're going to get basically the ratio of this is going to basically equal 0. So what Boltzmann has shown us is to have a configuration of the system where they're bouncing around changing. Look at this, you basically drop to 0, and I think this one ends up being something like right in here. It's a very thin window, and it's centered around 1162, right? So if the system was to ever so slightly have a few collisions and go slightly to this way or this way, populating N3, the chances of it keeping and going any further are almost slim to none, and the next few collisions will bring it back very close centered to what's called the dominant configuration at all times. So if we were to sit there and take 1 trillion pictures, magical pictures that let us see the number of particles that are in their first, second, or third, the only time you ever look at the system, you're basically going to see this type of configuration at all times. You're never going to see something out here or here. So this is only for 10,000 particles. What he basically proved is if you have a mole of gas, do you have any idea how thin this little peak is going to be? Which means every time you look at it, you're always going to see the dominant configuration, the way that they've distributed the energy amongst the particles. And that is why, at the end of the day, Boltzmann ended up saying that entropy will be related to the number of ways that the dominant configuration can be done. And there's this Boltzmann's constant. So the entropy of the system is, whenever you look at it, you're always going to see the dominant configuration anyway. So the entropy of that system is what his formula calculates.